everybody! So today we're going to talk about chapter 4.3, which is the modern theory of the atom. And it's a bit more confusing than the models we've talked about up until now, but it is a pretty cool thing. So we last left off with Rutherford's model of the atom. And Rutherford did the gold foil experiment, and he discovered that there is a small positively charged nucleus in the center of the atom, and then the negative electrons are found outside the nucleus moving all around. There was a scientist named Bohr, and he mostly agreed with Rutherford except for one little detail. Bohr noticed that certain elements gave off different colors when they were burned or when you passed electricity through them. And Rutherford's model really couldn't explain this. So Bohr went a little bit further in terms of describing the electrons in the atom, and he came up with the idea of energy levels. So an energy level is the possible amount of energy that an electrons in an atom can have. And you can see this model in the background here is a model of Bohr's atom. It still has a small positively charged nucleus, but it has these rings that are at set distances away from the nucleus, and that's where the electrons are found. So the rules of energy levels are this. The farther from the nucleus, the more energy an electron has. An electron in an atom can move from one energy level to another when the atom loses or gains energy. And this energy is usually lost or gained in the form of light. And the exact amount of energy gained or lost can be identified by a color of light. And this exact amount of energy also corresponds to a certain element. So this is where Bohr decided that this model would be a really great explanation for why different elements burn different colors. Now, let's talk a little bit about light. You've all heard of the rainbow: red, orange, yellow, green, blue, violet, Roy G. Biv. But you probably didn't know that red light is the lowest energy of light in the electromagnetic spectrum, which is what we call the light spectrum. And purple light is the highest energy. Now, you usually think of red light as having really, really high amounts of energy because you associate red things with heat. But it turns out the hotter you get an object, the farther up the rainbow that color will change. So something that's yellow hot has more energy or is hotter than something that's red hot. And something that's blue hot is even hotter than something that is yellow hot. So the farther up this way you get into the light range, the more energy you have. So given that, and given our three rules of the electron levels, energy levels, talking about the closer it is, the more energy it has, let's compare two different elements. So on the right, you can see I have an element with one proton and one electron. So one proton means it has an atomic number of 1. So if you look at the periodic table, you would see that this element is hydrogen. And when we look at this electron, when it's way out here, it has a lot of energy. The farther away from the nucleus an electron is, the more energy it has. What that means is, if this electron were to change energy levels and go from a high energy level to a low energy level, it would lose energy. It gives off energy to go from high to low. In that process, if it's going from very far out to very close, it's going to let off light of a very high energy, probably blue or purple. Now, if we instead think about the electron going from, let me change my pen here, this energy level to this energy level, it's still losing energy because it's going from high energy to low energy, but it's not losing as much energy, so it's going to give off light with a lower energy than blue light, probably green or yellow. The smaller the jump, the lower energy of light, meaning the closer to red on the spectrum of the rainbow it will be. Now, the opposite can happen too. If we have a little baby electron hanging out right here, E- electron, and that electron wants to move from a low energy level to a high energy level, it needs to absorb energy. It needs to take in energy to go from low to high. In this case, it's jumping a pretty far distance, a pretty big energy level gap. So it needs to absorb energy of a high energy, or it needs to absorb light of a high energy, in this case probably blue or purple. Now if we look over here at this element has 1, 2, 3 protons in it, which means it has an atomic number of 3. And if you look on the periodic table, you'll see atomic number 3 is the element lithium. And just looking at this, I drew this, so this is not necessarily accurate for a lithium atom, but I drew it to represent to you the fact that the energy levels inside an element are unique. So the energy levels inside a hydrogen atom are not the same as the energy levels inside a lithium atom. So in this case, if our electron goes from here to here, this is a much smaller energy loss than it was to go one energy level down over here, meaning it's going to lose light of even lower energy, like red. And these different colors are totally unique to these elements, which kind of describes what that element is. So we talked about an element being defined by how many protons it has, but you can identify the element if you pass electricity through it by looking at the colors of light that it gives off, because that will tell you exactly the energy levels that it has, and that will be unique to that element. So this is how energy levels work, and this is the idea that Bohr came up with, and Bohr was a really, really brilliant guy. But as scientists looked deeper, they agreed that there are energy levels, but they disagreed that the electrons were set in these orbits. So we would call this a planetary model of the atom. The proton in the center in the nucleus would represent the sun, and the electrons going around it would be like the planets in orbit. They are set in one orbit and always move along those lines. But as time went on, scientists said, you know, I don't think that's true. In 1924, there was a guy named de Broglie, Louis de Broglie, and he came up with this idea that particles of matter also act like waves of energy. And it sounds really crazy, and there's a lot of really complicated science and math behind this. But a few years later, Schrodinger said, you know what, that's totally true. And if we look at the electrons in an atom, I can come up with some mathematical equations that represent that wave-like behavior. This led us to what we now accept as the model of the atom in current times, and this is called the electron cloud model of the atom. We still have a small positively charged nucleus where all of the protons and neutrons reside, and all of the electrons are found outside of that nucleus. But unlike the electrons moving in one set line around the outside, the electrons exist in a probability space. And this is really hard for some people to wrap their brains around, but stay with me. So an electron cloud is a visual model of the most likely locations where an electron could be found. So it's not one line that the electron is moving on, it's a space where the electron could be found. And the space where an electron is most likely to be found is called an orbital. So the electron cloud is a visual model of that orbital, where that electron is most likely to be found. So I have a few pictures here. And the first one is an electron cloud model of the hydrogen atom. So you can see this little red dot is the nucleus. And all around here is shaded in blue. And this big blue circle represents everywhere that the electrons could be found. They're more likely to be found closer in, which is why it is a paler color than they are farther out. But the electrons at any given moment could be in any of these spaces. So we would call this the orbital for a hydrogen atom. It's this circle. And this visual representation, this picture, is the electron cloud. Now this is a more complicated picture of an orbital. So Unlike in hydrogen, where the electron is likely to be found in a sphere around the nucleus, this is a really crazy looking shape, which is telling us if the nucleus is right in the center here, the electrons are likely to be found anywhere in these funky looking shapes. These are the orbitals. These are telling us that the electrons are likely to be found in any of these places at any given time. And this visual picture here is what we would call the electron cloud. So it's really weird because we're not saying the electrons are in this space. We're saying the electrons are likely to be found in this space, and they could be found anywhere within that space at any time. But whether we're talking about orbitals in the electron cloud model or paths around the nucleus in the Bohr model, atoms always like to behave in certain ways. For example, electrons like to be in the most stable place. And in an atom, this is the orbital or path with the lowest energy, meaning closest to the nucleus. So if we look back at our picture here, the shading is lighter in the center of this orbital, in the center of this electron cloud model, because that is where the electrons are likely to be found. That's the most stable place, the lowest energy. The farther out you get, the less likely the electrons are to be there, but they could be found anywhere in this space. And we call this lowest possible energy level the ground state. And that's pretty easy to see in our picture here. The ground state in the Bohr model is what is obviously the closest path to the nucleus. So in this case, the ground state would be in, whoa, what's going on here? The ground state would be on this path right here. This is the one with the lowest energy. It is closest to the nucleus. This is the ground state. Whoop. Come on. My computer's doing funky things here. And the overall arrangement of the electrons in their orbitals or in their paths is what we call the electron configuration. So if I had an electron here and I have one electron here, that would be the specific electron configuration for those two electrons in this atom at that time. Obviously, this is not the most stable configuration because this electron is farther away from the nucleus than it could be or it should be. But that would be the configuration. So that is our modern model of the atom. And while we are going to talk a little bit more about electron clouds, we're mostly going to focus on the Bohr model of the atom, meaning this model with the rings and the specific energy levels. But know for your future science training and science education that the Bohr model, while it's pretty easy to understand and it's a really great way to observe elements interacting with the world, we have a more sophisticated model of the atom that we actually follow today.